Welcome back to Hypnosphere. This is a quiet space for unhurried curiosity, a place to rest among ideas and let the science of the universe settle over you like a soft blanket. If you are listening at the edge of sleep or in the gentle lull of a late afternoon, feel free to loosen your attention and let the words drift by. And if you feel comfortable, you can share in the comments where you are listening from and what time it is for you right now. Someone might be hearing this in the small hours beneath a winter sky. Someone else might be on a lunch break, the sun warm on their shoulders. Each of us under the same cosmic story. Tonight, we slip into one of the universe's most transformative chapters. It is a story of endings that become beginnings, of sudden light that fades into lasting change. It is the science of supernovae, the death and rebirth of stars. The night sky feels calm to us. Stars hold their places like beads of frost, and over a single human lifetime, most of them barely budge. Yet the interior lives of stars are anything but still. For millions to billions of years, they draw energy from nuclear fusion. Hydrogen becomes helium, helium becomes carbon and oxygen, and so on, in layers that deepen as the star ages. At every step, the star balances its own gravity with the pressure of hot, luminous gas. Imagine a long inhale and exhale, held in perfect poise. Gravity pulls inward. Heat pushes outward. The star lives in that equilibrium. But equilibrium is not forever. In the heart of the most massive stars, an invisible clock counts down as fuel is consumed. As the chemistry of the core shifts, pressure wanes, and the star must find a new balance. One day it cannot. What follows is swift. The star's interior changes faster than language can easily capture. A failure of support that leads to collapse, a burst of light, and a spreading wave of energy that carries the star's story to the wider galaxy. We call this ending a supernova. In the night sky, you can outshine a galaxy for a brief while, then fade, leaving behind a remnant that glows and expands for thousands of years. A supernova is not only an ending. It is also a workshop where new elements are forged, a kill where atomic bonds are reshaped, and a wind that stirs the interstellar medium. The iron in your blood was assembled in the furnaces of ancient stars and sent into space by events like these. Calcium in your bones, oxygen in your lungs, the phosphorus that helps your cells communicate, all carried outward by the aging of stars and by their final luminous breaths. There are two broad ways a star meets this fate. One path is the collapse of a massive star at the end of its life, when its core can no longer sustain fusion. The other path is the thermonuclear runaway of a compact star, a white dwarf, pushed to a critical threshold by a close companion or a collision. These two mechanisms produce different signs in the light of the supernova, different chemical fingerprints, different remnants. For now, it is enough to hold the idea that supernova are both a closing and an opening. They end a star's particular story, but in doing so, they release materials and energy that help other stories begin. Gas clouds are compressed and stirred. New stars are born. Planets take shape. And life, at least in one small corner of the cosmos, becomes possible. Tonight we will go slowly. We will visit early observations of strange new stars that appeared and then faded. We will step into the laboratories and observatories where people learn to read the spectra of starlight. We will follow the thread through core collapse, through shock waves and neutrinos, through the quiet, fierce logic of a white dwarf's runaway fire. And we will look outward to the filaments of supernova remnants, the dust and molecules that form within them, the way a galaxy breathes through these events. Finally, we will return home to our own world and bodies, to the trace of supernova written into our cells. Let your shoulders soften. Let your breath be easy. Picture the night above you, even if you cannot see it. A great dark ocean patterned with living stars that are constantly becoming, evolving, and eventually letting go. In that letting go, there is a kind of generosity. There is a calm, luminous release. And there is a trail we can follow through history and science to understand how supernovas shape the universe and us. In the soft light of that understanding, we begin with the earliest witnesses, people who saw sudden stars appear where there had not been stars before, and wondered what it meant when the sky changed. In a time before electric light, the night sky was an intimate companion. Its slow motions marked seasons and set rhythms for planting, sailing, and story. When something new entered that familiar pattern, it was startling. Ancient astronomers called them guest stars because they appeared uninvited and then moved on. One of the most famous guests arrived in the year 1054. In China, court astronomers recorded a brilliant star in the constellation of Taurus. It was visible in daylight for weeks, and at night for nearly 2 years. In Japan, and possibly on rock art in the American Southwest, echoes of that bright visitor remain. Today, we point telescopes to the same patch of sky and see the Crab Nebula, a delicate tangle of filaments expanding from that long-ago burst. At its heart, a neutron star spins 30 times each second, sweeping beams of radio and light like a lighthouse. The ancient notes and the modern image align, a 1,000-year bridge of careful looking. Centuries later, in 1572, Tycho Brahe watched another sudden brightening, this time in the constellation Cassiopeia. He measured it precisely, night after night, noting that it did not shift against the backdrop of stars the way a nearby object would. This meant it was far beyond the moon, out where the stars lived, in a realm that many had believed was unchanging. Tycho's book, The Stella Nova, challenged that belief. The sky could change. The heavens were not a crystal sphere. The universe allowed for creation and transformation. A few decades after Tycho, Johannes Kepler recorded a similar event in 1604, noting its steady fade, its colors, its position among the stars. Kepler's supernova was the last such naked-eye event recorded in our Milky Way. In the centuries that followed, telescopes grew in size and clarity. The 19th century brought spectroscopy, a way to disperse starlight into rainbows and read the lines within them. Each chemical element leaves a pattern in that spectrum, like a signature. When astronomers held the rainbow of a star up to this spectral comb, they could see which elements were present and in what relative amounts. It was like learning the alphabet of light. Suddenly stars were not just points, but places with specific compositions and behaviors. With spectroscopy, differences emerged between novae and supernova. Novae are eruptions on the surface of a white dwarf in a binary system, a temporary brightening. Supernova were something else, far more energetic, with spectral features and lasting remnants that pointed to deeper change. In the 1930s, Walter Baade and Fritz Zwicky proposed that supernova marked the transformation of an ordinary star into a denser state, what they called a neutron star, and that such events could be the source of cosmic rays. It was a bold idea, landing ahead of the evidence. But it fit with the growing understanding that atomic nuclei and nuclear forces were at the heart of stellar life. The word supernova suggested kinship with novae, but the scale was different. A nova is like a flare on a cold winter night, bright and contained. A supernova is the full clearing of the hearth, a deep rearrangement of the house. Through patient observation, astronomers learned to separate them. They also began to notice that not all supernovae were the same. Some showed hydrogen lines in their spectra. Others did not. Some brightened and faded with a predictable shape to their light curves, the slow arc of their illumination plotted over weeks and months. Others varied. By the mid-20th century, these patterns had settled into categories that reflected real physical causes. Type II supernovae showed hydrogen lines, indicating they were massive stars that still held their outer envelopes when they died. Type I supernova lacked hydrogen. Among those, Type Ia showed a strong silicon absorption line around a specific wavelength and had light curves that were strikingly similar from one event to another. Type Eben IC lacked hydrogen, and in the case of IC also lacked helium, pointing to massive stars stripped of their outer layers by stellar winds or interactions with a companion. Imagine crowded shelves of observations, glass plates bearing the silent traces of distant events. Each photographic curve is a whisper from a star. There is something tender about this accumulation of light from past decades, stored and revisited. The science grew not from a single moment, but from many nights, and many people who returned to the same patch of sky to see what had changed. Even as these patterns became clearer, the deeper mechanics remained mysterious. How exactly does a massive star collapse, and what launches the outward shock that people on Earth can see from so far away? How does a white dwarf in a binary system go from stable to runaway fire? The answers to these questions would come from both theory and observation, from equations that track the pressure and temperature in a star's core, and from rare, nearby supernova that offered more than light alone. The night of February 23, 1987, would bring one of those rare gifts, and with it, a different kind of messenger. To understand what dies in a core collapse supernova, picture a star at least 8 times the mass of the Sun. It shines for millions of years, far shorter than the Sun will, because its greater weight squeezes the core, raising temperatures and accelerating fusion. The star's interior develops an onion-like structure. In the center, helium made from hydrogen burning fuses into carbon and oxygen. When that fuel dwindles, the core contracts and heats, and new shells ignite. Carbon burns to neon, sodium, and magnesium. Neon burns to oxygen and magnesium. Oxygen burns to silicon and sulfur. Silicon burns to elements near iron. Each step occurs at higher temperatures and over shorter timescales. In massive stars, the silicon burning phase can last days. The layers above continue to fuse lighter elements more slowly, like the outer rings of a tree still quietly growing. Iron and its neighbors on the periodic table do not give energy when fused in the pressure conditions inside stars. They sit near the peak of the binding energy curve. Fusing them consumes energy rather than releases it. That is the end of the line for a star's core. As iron group nuclei build up, the pressure support becomes precarious. Electrons, the light particles that provide much of the pressure through their quantum resistance to being squeezed together, are captured by protons, producing neutrons and neutrinos. This electron capture reduces the pressure and accelerates collapse. The core contracts with astonishing speed, racing inward at a significant fraction of the speed of light. In a breathless instant, the core density exceeds that found in atomic nuclei. Neutron degeneracy and nuclear forces stiffen the matter, and the collapse halts, rebounding slightly. This halt and bounce sends a shock wave outward into the remaining and falling layers. That would seem to launch the supernova. In early simulations, however, the shock stalled as it lost energy to the breakup of heavy nuclei and to an outflow of neutrinos. These nearly massless particles carry away most of the gravitational energy released in collapse, a flood that slips through matter almost without a trace. The challenge for decades was to understand how the stalled shock regains strength. The emerging picture includes neutrino heating behind the shock, turbulent convection that helps carry energy, and large-scale instabilities that slosh and spiral the shock into motion. Rotation and magnetic fields may assist in some cases. It is a complex dance, sensitive to the chaotic flow of hot, dense matter. In 1987, a blue supergiant in the Large Magellanic Cloud reached the end of its life. We call it SN 1987A. It was close by cosmic standards, about 168,000 light-years away, a neighboring dwarf galaxy that orbits the Milky Way. On that February night, underground detectors in Japan, the United States, and the Soviet Union recorded a sprinkle of neutrino interactions, just a few dozen in total, across all instruments. Those faint clicks arrived hours before the light of the supernova reached Earth, because the neutrinos escaped almost immediately, while light diffused more slowly through the star's outer layers. The timing, the energies, the coincidence across independent detectors all fit the predictions of core collapse. It was a quiet confirmation of a violent interior process, a soft rain of particles telling us what had happened deep in the heart of a star. SN 1987A also provided a rich record of light and evolving structure. It rose to a peak brightness, faded, and then showed lingering glow from radioactive isotopes such as cobalt-56 decaying into iron-56. Glowing rings around the supernova, illuminated by the blast wave, traced out material shed by the star before it died. Over the years, telescopes like Hubble watched the shock interact with those rings, bright spots blooming where dense knots were struck. It became a living laboratory, one we are still studying, patient as the expanding wave makes its way through the star's past winds. Not all massive stars that die leave the same remnant. If the core is not too heavy, the result is a neutron star. These can reveal themselves as pulsars, spinning rapidly and emitting beams of radiation that sweep across space with metronome precision. In other cases, if the core is sufficiently massive, even neutron degeneracy cannot hold back gravity, and the core collapses further to a black hole, a region from which light cannot escape. There is a spectrum between these outcomes, shaped by rotation, composition, and environment. With sensitive X-ray and radio telescopes, we can find neutron stars embedded in their remnants, or measure the empty center where a black hole likely took shape. The other main path to a supernova begins not with a giant, but with a small, dense star called a white dwarf. White dwarfs are the final state of stars like the Sun. After exhausting their hydrogen, such stars swell into red giants, shed their outer layers, and leave behind a compact core about the size of Earth, supported by electron degeneracy pressure. By itself, a white dwarf is stable, its carbon and oxygen atoms packed tightly. But in a close binary system, a white dwarf can draw matter from a companion star, or two white dwarfs can spiral together and merge. If conditions bring the white dwarf near a critical mass, around 1.4 times the mass of the Sun, known as the Chandrasekhar limit, the conditions in its interior shift. Temperature rises, and because the pressure in a degenerate gas does not depend primarily on temperature, the star cannot expand to cool itself. The stage is set for a thermonuclear runaway. Carbon ignites in spots within the white dwarf, a flame that moves subsonically at first, a deflagration. In some models, this transitions into a detonation, a supersonic burning front that sweeps through the star. The nuclear fusion liberates a tremendous amount of energy in a fraction of a second, unbinding the star entirely. There is no remnant neutron star or black hole, only an expanding cloud of newly synthesized elements, including large amounts of nickel-56 that decays to cobalt and then to stable iron, powering the light curve. The spectral signature shows no hydrogen, and the silicon line marks the unmistakable physics of silicon-burning products. These are type Ia supernovae, and their remarkable uniformity in brightness, with subtle correlations between the shape of their light curves and their peak luminosities, gives them a special role. They serve as standardizable candles, distance markers across the universe. Both paths, core collapse and thermonuclear runaway, write in light and in debris the conditions of their birth. By studying the timing and color of the light, the absorption and emission lines, and the aftermath, astronomers read that story. A collapse tells of mass, of layered fusion, of a core's surrender to gravity and a resurrected shock. A white dwarf's end tells of a critical mass, a nuclear flame, a complete unbinding. In both, neutrinos whisper of the interior, while shock waves sculpt the outside world. From here, we step outward into what these endings leave behind, into the filaments and knots of supernova remnants, into dust grains forming in expanding gas, and into the way a galaxy breathes through these quiet storms. Walk through the remains of a supernova in your mind. You might be looking at the Veil Nebula in Cygnus, a lace of luminous filaments set against the black of space. Or the Crab Nebula, a web of tendrils threaded with synchrotron light, a soft glow from electrons spiraling in magnetic fields. Or Cassiopeia A, a rich, three-dimensional blossom of clunts and arcs, each carrying a different chemical signature. These remnants swell slowly over thousands of years. The blast wave, invisible on its own, runs ahead of the visible filaments and heats the interstellar gas. Behind it, a reverse shock travels inward through the ejected matter, compressing and illuminating the layers the star expelled. Within the cooling ejecta, dust grains can form. It may seem counterintuitive that such a hot, violent event births delicate things like dust, but as gas expands it cools, and atoms find each other. In SN 1987A, astronomers detected molecules like carbon monoxide and silicon monoxide as the ejecta cooled, and then evidence for new dust. Dust grains are small, but collectively they shape how light moves through galaxies. They provide surfaces for complex chemistry, including the steps that lead from simple molecules to the ingredients of life. When we examine the oldest meteorites in our solar system, we find tiny grains with isotopic ratios that do not match the sun's. Some of these pre-solar grains bear the fingerprint of supernova. They are literal fragments of ancient star deaths that found their way into the cloud that formed our sun and planets. Supernova remnants are also factories for high-energy particles. At the shock front, charged particles can bounce back and forth across tangled magnetic fields, gaining energy each time. This process, called diffusive shock acceleration, is a leading explanation for the origin of many cosmic rays, the fast-moving atomic nuclei that reach Earth from space. We see gamma rays from supernova remnants that trace the collisions of these energetic particles with gas, producing a glow that tells us where and how they are being accelerated. The remnants are not just ashes. They are engines, humming softly across thousands of years, feeding energy into the surrounding medium. All of this plays into a broader ecology. A galaxy is not a static arrangement of stars and gas. It is a living environment where energy flows, matter cycles, and feedback regulates growth. Supernova are a key part of that feedback. They stir and heat gas clouds, preventing too much gas from decaying into stars at once. They also compress certain regions, triggering new star formation. The balance of these effects shapes the rate at which galaxies turn gas into stars. The thickness of the star-forming disk, the chemical gradients from center to edge. It is like rainfall and wind in a forest. Too little, and the air becomes stagnant. Too much, and young saplings are uprooted. With the right rhythm, the forest breathes and renews. The chemistry written by supernova is fundamental. Core collapse supernova are rich in oxygen, magnesium, silicon, sulfur, calcium, and some iron. They seed the interstellar medium with these alpha elements that form during the star's life and final moments. Type Ia supernova produce large amounts of iron peak elements, iron, nickel, and cobalt. In the history of a galaxy, Early generations of massive stars explode quickly and enrich gas with alpha elements. Later, as white dwarfs in older stellar populations reach their critical moments, Type Ia events add iron gradually. By measuring the abundances in stars of different ages, astronomers can read the timing of this enrichment, a chemical clock that reveals a galaxy's past. There is also the question of the heaviest elements, those beyond iron that require rapid neutron capture. For years it was thought that core collapse supernova might host this R process in the matter that squirts out of the poles or in neutrino-driven winds. Some supernova may produce a portion of these elements, especially if rotation and magnetic fields are strong. But evidence has mounted that many of the very heavy elements, like gold and platinum, are forged in collisions of neutron stars. In 2017, gravitational waves and light together revealed a kilonova, the glow of neutron-rich ejecta producing heavy elements. Both processes likely contribute in different proportions over time. The picture is still being refined. The important theme is that deaths of stars, whether by collapse or by merger outcomes, are responsible for the richness of the periodic table we experience on Earth. Type Ia supernova carry another gift. Because their peak brightness correlates with the shape of their light curve, once calibrated with nearby examples, they can be used to measure distances far across the universe. In the 1990s, teams led by Saul Perlmutter and by Brian Schmidt and Adam Rees used Type Ia supernova to map how the expansion of the universe has changed over time. To their surprise, distant supernovae were dimmer than expected, implying that the expansion is accelerating. This led to the concept of dark energy, a pervasive component of the cosmos that affects its large-scale dynamics. A quiet pattern in the light of dying stars became a ruler for the cosmos and opened a route to one of the deepest mysteries in physics. Think of a single supernova, then zoom out to the populations of them in a galaxy, and then farther to clusters of galaxies and the growth of structure in the cosmic web. Energy released in stellar deaths feeds back into every scale. It is as if the universe inhales through gravity, gathering matter into stars, and exhales through supernova, stirring and enriching the spaces between. Even the shape of spiral arms, the flicker of star formation in dwarf galaxies, the winds that blow from starburst regions, all carry the imprint of these events. When we look at a galaxy like the pinwheel in a telescope image, the pinkish knots where new stars are forming are often accompanied by the ghostly arcs of shells and bubbles created by winds and supernova. The scene is busy and serene at once. And all of this remains connected to a human scale through simple, quiet words. Iron, oxygen, calcium. Light that rises and falls in weeks. Dust that glows faintly in the infrared. A star that was once as steady as any we see, reaching the end of its balance and letting go. In that letting go, the future is fed. To move from this grand tapestry back to us, we only have to think about how our own solar system took shape and what traces of star death we carry within our bones and blood. 4.5 billion years ago, a cloud of gas and dust in one spiral arm of the Milky Way began to collapse. It was not pure hydrogen and helium. It had been enriched by previous generations of stars. Within the cloud were grains that had formed in supernova ejecta, and radioactive isotopes that had been created not long before. As the cloud spun and flattened into a disk, the sun formed in the center, and planets coalesced from the remaining material. In meteorites, we can still find the daughter products of short-lived isotopes like aluminum-26 and iron-60, evidence that freshly minted radionuclides were present during those early days. Their presence points to a nearby source, perhaps a supernova in the neighborhood, that seeded the nascent solar system or triggered the collapse of the cloud. When you hold a small iron object, you are holding the echoes of that story. The iron in your hemoglobin binds oxygen that enters your lungs with each breath. That same iron nucleus was stitched together in the final stages of nuclear fusion in a massive star, or in the thermonuclear ash of a white dwarf that unbound itself. The calcium that hardens your bones was fused in a shell around a dying star's core. The oxygen you breathe, is silicon beneath your feet in sand and stone, the sulfur that helps proteins take shape, all arrived through stellar life and death. Supernova also reach across to habitability in gentler ways. They help create and distribute complex molecules in space. They regulate star formation so that galaxies like the Milky Way maintain long-lived regions where stable planetary systems can form. There is a balance here. Too many nearby supernova could strip atmospheres or bathe a planet in radiation. Too few and the chemical diversity that makes life possible would be thin. Earth sits in a wide, quiet lane between spiral arms, where nearby supernova are rare on human timescales. When Betelgeuse in Orion eventually ends its life, it will be a sight for the ages, but it is far enough away that it will pose no hazard to life here. It is a gentle thought that the universe can be both dynamic and hospitable. In the next nearby core collapse supernova, our instruments are ready. Neutrino detectors, deep under mountains and ice, wait for that soft, early rain of particles. They can provide the first alert, a whisper that a star has collapsed even before the light curves begin. New telescopes on the ground and in space will watch the rise, the shift in color, the spectral lines opening and evolving. Radio arrays will track the shock as it plows into the surrounding medium. X-ray telescopes will see the hot interior. In gravitational waves, we may glimpse the asymmetric motion of matter inside the dying star, a new way of listening to an old song. And in the dust that forms in the aftermath, we will watch the building blocks of future planets begin to grow. The knowledge that stars die and in dying give rise to new stars and to worlds like ours offers a gentle orientation. It says that change is not only loss. It can be release and renewal. It says that we are not apart from the universe, but expressions of it. There is a steady humility in that view, and also a quiet joy. Imagine looking up at night and recognizing not only constellations, but processes. The long balance of fusion and gravity in a star like Sirius. The young heat of regions like Orion, where new stars are kindling. The hushed, thin glow of remnants, where a star ended and something else began. Each site is a chapter of one book. As you settle for sleep or rest your eyes, you might feel the rhythm of your breath. Under it, the slower breath of the sun's magnetic cycle, the slower still breath of star birth and death across the galaxy. Supernova are part of that rhythm. They are the exhale that enriches space, the warm wind that clears the ground for new life. They remind us that endings can be generous, that the universe is ancient and evolving, and that we are made of the same matter that once burned in stellar hearts. Thank you for spending this time in Hypnosphere, for letting your curiosity rest among the stars. If this quiet journey helped you relax or offered a new way to see the sky, you are welcome to subscribe and join us again. There is more to explore, gently, patiently, together.